All right. Well, welcome everybody. So this is the physics department's annual Nobel Prize lecture. So this lecture series was started in the department a few years ago in 2022, and is aimed at having someone explain to the community the science behind this year's Nobel Prize. And so this past year, the Nobel Prize in Physics was awarded to Hopfield and Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks. Now, that doesn't sound much like physics, so we need the help of an expert to explain to us how this could possibly be connected to physics. That expert is John Sous. John is an assistant professor in applied physics and also the Energy Sciences Institute. He's also affiliated with the Yale Quantum Institute and the Institute for Foundations of Data Science. John joined Yale in 2024. Before that, he was an assistant professor at UC San Diego. He also held postdoctoral fellowships at Stanford and Columbia. And before that, he received his PhD in physics from the University of British Columbia in 2019. John is a rising star, and he was recently awarded the Air Force Officer of Scientific Research Young Investigator Award. And his research really sits at the intersection of several different areas: condensed matter physics, quantum physics, and artificial intelligence. And so this puts him in a perfect position to explain to us how the most recent Nobel Prize is connected to physics. So take it away, John.
Thank you, David. So, can you hear me in the back? Yeah, okay. So thanks for this very kind introduction. I am definitely not an expert. So maybe I want to preface the talk by saying that David told me this is a talk for our undergrads. So keep that in mind. Really, my goal here is to make this very accessible to our undergrads who are going to move on to, in the very near future, to jobs either as PhD students doing research and will probably interact with machine learning, or in industry as quantitative finance or tech or some other field where machine learning is basically plays a big role in almost all aspects of life. And what I'm going to try to do today is to tell you my biased view of how we should think of machine learning or AI and physics today, right? Though I will do this, I will try to give due credit to Hopfield and Hinton and present sort of a big picture view of their contributions and how they connect to physics and why that is a Nobel Prize in physics, especially for Hinton, who's not a physicist. Hopfield is clearly a physicist. Okay, so with this in mind, let me get to it. When we think about physics, how do we define physics? In my personal view, physics is just the science of explaining the behavior of natural systems. You know, and you can go over all things here. The fields I'm aware of and I'm intimate with, statistical physics and condensed matter, but that applies to cosmology, high energy, AMO, biophysics. We have some reality. It's the natural system. Systems behave in whatever way. That's what we observe experimentally. And our job as experimentalists is to understand this better, and as theorists to provide models that predictively and testably demonstrate the observed behavior. That's how we understand physics. Okay, how about artificial intelligence? In the most primitive way, we can think of a neural net or an architecture of learning as something where I have inputs, that's the data, that's what's observed for whatever reason in this world. It goes through this infrastructure and I get an output layer. If you want to think about this in the most simplistic and most effective way, the output is basically a function of the input. It's a very complicated function. It's built in a very complicated way, but my goal is to get that function so that when I want to understand what could happen if I change the input, I have a new input, I just plug it in into this function, and it tells me what could happen. In reality, it's sort of maybe in an unfair description, it's like a form of high-dimensional fitting. It really is fitting in very high-dimensional space. But of course, there are surprises that, as we see in today's world.
Don, can you, sorry to disturb you, but could you please flick the slides on Zoom? That would be much appreciated.
Make the slides on Zoom?
Yeah, they're clipped.
Yeah, how do I do that?
Minimize the bar on the cases, screw it to the side.
Yeah, I don't know.
Just try to reshare. I mean, it looks
Okay, so stop sharing. And
stop share first.
let me share. Let me share my desktop instead of the presentation. And then we see new slideshow. How about this? Is that better?
Yes, it is much better. Thank you.
Okay, sorry about that. Okay, so just going back to it, in physics, we really want to explain the natural world. In machine learning, we have this kind of infrastructure. That's how we can view it in modern times, which is trying to learn a highly non-trivial behavior or correlations in the input so that when we have a new input, we can make predictions. But we really could think about this type of system as just another artificial system. Why do we have to think about it as just a computer program, right? It could really be viewed as another experiment. In fact, practitioners in this field, when they run simulations, they call them experiments. They don't call them theory. So if I think about this as an experiment, exactly as in the modern era, we think about experiments at very low temperatures, at ultra cold temperatures with fermions, fermionic atoms, trying to simulate a Hubbard model as some ultra quantum matter simulators. We can think about those as some type of matter. There's a large number of degrees of freedom. Statistical physics definitely plays an important role. And there is, I think it's fair to say, there's poor understanding of how these things function. They work, but how they work, why they work, when they work, there's a lot of empirical advances, but they're not always principled or understood. So in that way, perhaps I would like to propose, and I don't want to come off as arrogant or anything. I'm not the first person to think about this. There are people in the machine learning community who've been saying this and they don't do any physics, but perhaps we should think about physics as the science of explaining the behavior of natural and artificial systems. Then it's very natural to think about neural networks and transformers and all the spiel within this realm of physics. And again, the natural systems, we all know what we care about, the universe, condensed matter, AMO, quantum information, and so forth. But in the artificial systems, artificially assembled computing units, i.e. neural networks, would constitute a very important example. There might be more future examples. I don't know. So this is just a proposal of how we can unify this. Now you will see that this is actually natural in the evolution, in the historic evolution of the contributions of Hopfield and Hinton, even though I don't think this, to the best of my knowledge, it wasn't really made as a concrete point at any point in that history. And so to do this, I thought that it would be kind of cool to give a history, a brief summary of the historic developments in machine learning. Maybe that would be useful for us in general as a reflection on history, but also because they're just interesting. So this is my rough history of neural learning that I extracted by Googling and looking at Wikipedia. And so there was apparently an idea of a perceptron or some form of a neural network that was proposed by a psychologist known as Rosenblatt. And this was in the early 60s or the late 50s and early 60s. And it received a lot of attention, and there were a lot of hype and promises about what they could deliver. And the military and other funding agencies really funded, poured money into this, but they couldn't deliver. And my understanding, I'm not certain that this is true, but I think it's probably fairly accurate, is they did not know how to train these things. The idea of gradient descent and backpropagation was not very transparent to them. So they can build things, it's kind of inspired by neuroscience, by how the brain should work and some hypothesis, but how do we actually use this for any computation was not clear. And that failure to meet these promises triggered what is known as the first AI winter. This is a period that extends roughly from 1974 to 1982, when funding dried out and it was very negative and undesirable to talk about AI. People didn't take you seriously if you talked about AI. And there were some researchers, but it wasn't really mainstream of science. And that era ended by Hopfield's work. What Hopfield has accomplished, if you want to summarize it in a few lines, in my own understanding, is he managed to explain that a recurrent network, so some connection, I will get into this in more detail in a little bit, some connection of these neurons is described by an energy function. And then the update rule to update the parameters of that function, which people kind of used, inspired by psychotherapy or neuroscience, it's known as the HEP rule, corresponds to taking steps down that energy function. And then learning will eventually get you to a local energy minima. And in that local energy minima, you have stored information about the data. You've memorized the data, right? And there are, of course, some interesting features about this in particular. Now that you've memorized certain patterns in your data, if you have some corrupted data, right, that is a small perturbation from your data, the model will be able to figure out that right local minimum by gradient descent, because these are attractors of dynamics, attractors of motion, and so you will be able to get memory retrieval. So in a hardware sense, that's very powerful, because if you wanted to go right now and implement a dictionary, associative memories are a form of a dictionary, you can do that in Python, but if you have hardware damage, you're done. You can't do much, right? The information is gone. But this is telling you, no, there's actually an architecture we can build that with some corruption of the data, we can still retrieve the memories. Then in '84, Hinton, who is a psychologist and a computer scientist, amongst other things, and Sujonsky, I'm not sure if I'm pronouncing his name correctly, who's a biophysicist, and Ackley, they discussed Boltzmann machines. And in a one-line summary, a Boltzmann machine is some architecture that is really closely resembles Hopfield. It's actually inspired by Hopfield, and models the data distribution. However, this Boltzmann machine is very expensive to train, to actually get it to work as desired. So there was not so much progress, and that triggered the second AI winter. And according to some articles I found online, actually during that second AI winter, researchers were kind of not inclined to talk about AI. They would reframe their work as something else, machine learning or neuroscience or whatever, because of the drought of funding that was associated with this. However, Hinton and others prevailed. They kept working on this. And in 2002, Hinton discovered an efficient algorithm for training restricted Boltzmann machines. So Boltzmann machines are a very type of general architecture, but if you restrict them in some way, he's not the one who proposed to restrict them. There's a different person, I believe he's a scientist. If you restrict them in a certain way, you actually can train them efficiently. And so that triggered one example of how we train a small network. And then going on, there's a lot of developments, but I think 2006 is a very important year, because in 2006, he thought of the idea of stacking multiple restricted Boltzmann machines. So imagine I take every restricted Boltzmann machine and I pretend that it's a unit in another restricted Boltzmann machine, and I stack many of them together. And he showed that you can do this and get dimensional reduction, which is nowadays known as autoencoders, right? I have some high dimensional data. I discover a map to a low dimensional representation. I do computations in a low dimension, and then I do whatever I want to do later on. Maybe I decode so I can go back to the high dimensional representation when I want to extract observables, or what depends on what my goals are. Or I just want to understand how the data behaves. And so I want, instead of looking at data in high dimension, I want to be able to get an accurate two-dimensional representation, and I see where features cluster, right? Like principal component analysis. That's a method that basically in 2006 would beat already principal component analysis. And then fast forward to the future, AlexNet is a demonstration that you can do this, but with modern neural networks, with backpropagation and gradient descent, with GPUs. And to my understanding, that's really triggered intense research. There's a lot of different developments that coincide with this, like Google Translation and Google Translate and so on. And one could say in the 2020s, we're living the AI spring. So it's clear, I think, in that kind of high-level picture that statistical physics have played an important role in both Hopfield's and Hinton's discovery. Hopfield definitely used the idea of an energy function. You can think of the objective or the risk that we're trying to minimize the loss function in current architectures as some energy function, right? That goes back to Hopfield. And Hinton really did a lot of statistical physics for Boltzmann machines. So I want to give some due credit to Hopfield, to Hopfield and Hinton. So this is a summary of Hopfield's trajectory. Steve Gervin here is Hopfield's student, actually, so he may know more than I do. But let me just say that Hopfield got his PhD from Cornell in 1958 in condensed matter theory, or at the time known as solid-state physics, with Overhauser, who's known for the Overhauser effect, and some claim that he should have probably have been awarded the Nobel Prize, but he didn't. And Hopfield started the trajectory in my field, working on exotones and polaritones, but then there is an evolution towards systems biology. He really touched a lot of different fields, worked on electron transfer between biological molecules. I really don't know anything about this area, and then discovered kinetic proofreading, a sort of a self-correcting mechanism. But folks who really know this, I hear from Bill Bailey, for example, that you could see a coherent and natural evolution of ideas across the different fields as Hopfield eventually goes and discovered the Hopfield model, Hopfield networks, which is a contribution in neuroscience and also the basis of modern developments in machine learning and AI. Jeffrey Hinton, on the other hand, he obtained his PhD in 1978 in AI. That was actually a field, artificial intelligence, at Edinburgh under Longwood Higgins. Longwood Higgins is the theoretical chemist or a molecular physicist. Ironically, he's also the co-advisor of Peter Higgs. So there is some connection here with physics and quantum stuff, though I don't think really Hinton worked on anything like this, but definitely we see ideas of statistical mechanics imprinted in the way he thinks. And their contributions in machine learning are really too many to list. But I think if we want to credit him with something, it would be Boltzmann machines, and then the idea of dimensional reduction from building multiple stacks of restricted Boltzmann machines, popularizing the use of backpropagation, the AlexNet contribution, and many, many more contributions in modern times. Okay, so a natural question that one would ask is, Hinton secretly a physicist? And here is a slide I stole from David Schwab at CUNY. They organized these theoretical seminars, symposia at the CUNY Center in New York City. And this is a slide from 2010. And you can look at the speakers. This is Hinton. You look at all the other speakers. Basically, they're all either chemical physicists or condensed matter theorists or statistical physicists. David Reichman, James Cessna, Kurchan, David Sepperly. So really, he was already somehow mingling with the physics community at large in some form. And the title of the talk there is very telling: learning models with trillions of parameters. So that's in 2010. No one could do that in 2010, but I guess he had the foresight that this is going to come, right? So is he really a physicist? He's probably not a physicist, but as an outsider, the contributions really make sense within the big picture of what physics is all about. So let's now get a little bit into the science. And what I decided I'll do is, for the Hopfield model and Boltzmann machines, I'll give one slide intro, just big picture, and then I will kind of, in a second slide, try to connect it to what's going on today. Then I'll talk near the end of the talk about recent things that are happening these days and how we may want to view them as connected to physics, if we wish. Okay, so a Hopfield network is a recurrent network. So that means that each unit or neuron is connected to all other neurons except itself. So it's recurrent in the sense that the output of that neuron, J, for example, will go to I, but then I will do some processing and its output will go back to J. So there's some recurrence that's going on. And we refer, these neurons can take values, they're binary, can take values 1 or -1. So we refer to those as sigma I. the neurons, and INJ runs over the neurons, which run from 1 to n. We have n neurons. And the connectivity is all to all. And then we would like to learn, that's the data that we would like to learn, some memories, psi, mu. These are our memories. They're also binary information. And mu runs over the memories from 1 to k. So what Hopfield showed is that there is an energy function that describes this system. This is this minus the sum over I and j, sigma I, sigma j, with the matrix element that connects them, which is what we know in modern machine learning as the weights. So obviously, this is very telling why this is something that physicists would care about. This is a simple spin model. Right? It's a spin model with an all-to-all connectivity. There's a strong connection to spin glasses. We can understand a lot of that physics with spin glasses. In fact, the spin glass community remains to be interested in Hopfield networks and associative memories. The main contribution we want to think about here is Hopfield realized that if Wij is symmetric, so that means going from I to j is the same as going from j to I, which is the case in structure, there's an energy function, and the update rule, which I'm not going to tell you about right now, corresponds to taking steps down this energy landscape, this non-convex energy landscape. And if we keep going down, we'll eventually hit a local minimum. That's where we will have this pattern, the memory that we want to store, stored. So that's a form of memories as low energy. Now, if you want to retrieve, you might ask, why would I care about doing this, right? Of course, you have to imagine this is more than 30 years ago. So the level of computation is not what's going on now. The idea is I have now a form of associative memory. I can associate inputs with certain memories. What if I give you a corrupted image or a corrupted form of memory? Well, the idea is, since these are local attractors, I will eventually find the right memory. So I will be able, so I'm not error prone. I will be able to retrieve the memory even though if there's some corruption. So that's a very powerful idea. It's hardware proof. Yeah.
A picture of the neurons and their connections, which I can see very clearly. Where should I think of the memories as being?
The memories is your data, really. So you will adjust the spins, the values of the sigmas in such a way such that your local minima will be those memories, will correspond to those memories. Right? That's not what we do in modern machine learning. In modern machine learning, we adjust the weights. Here, the weights there is a nonlinear update rule known as the HEP rule that determines how you update this. So people apparently knew about that rule, but they didn't understand that this is going down an energy landscape.
So is K 2 to the n?
No, so that's a very good point. So this is now we're getting into details that I'm really not expert on, but in the original formulation, the number of memories you can store is linear in the size of the network, right? Though the space is exponential. There are now modern formulations that also Hopfield is involved in, let's say from 2016, so that's roughly 10 years ago, with a known researcher by the name of Krotov. He's an IBM. He's also a physicist, an ex-physicist, or you could say still a physicist. And they have managed to kind of reformulate this via different connectivities to show that you can now have exponential capacity. And actually, transformers is one class of such models that arise out of these models. So, in fact, one of the points I want to make is that you could, this is the consequences in modern era, you could think about associative memories and Hopfields, in some kind of more generalized version than what I explained to you as a unifying principle. Their work to show that transformers arise from these generalizations. Diffusion even, which at first pass does not seem to have any connection to this, could arise also from this. So this is all recent work as we speak, like even the diffusion work, I don't think is published, it's on the archive. So this is not stuff that's, well documented. It's still a topic of debate in the community. Right, so now what's the significance of that? Like why did Hopfield get the Nobel Prize? And I'm stealing here from Hinton's own words. I was teaching a class on the physics of AI. And so I took Hinton's class slides and I looked at them, and that's Hinton's view of what Hopfield have done. Hopfield realized thatWij's are, if they are symmetric, there will be a global energy function. So that's kind of the critical physics insight that Hopfield had in the understanding that we have, not being inside Hopfield's mind, obviously, of what enabled him to kind of make this contribution. And then the consequences of that is that now memories, these Sous, are local minima. So that's actually an implementation of memories as energy minima. And that means that we can access parts of a memory just, even if it's corrupted, by having just access to parts of it, not the full thing. We can start from a perturbation of the Sous, and then by going down the energy landscape, we'll find the appropriate Psi in the neighborhood. And that's robust against hardware damage because I'm not relying on hardware memory, right? Exactly like if you took a Python dictionary, you implement the dictionary, it's going to work. But if you have some, the memory, the chip is just not functioning, it's done. The memory is gone, right? So that's kind of the consequences of this impactful work. And if we want to connect it to modern times, exactly, I was answering Jack's question. Transformers and other architectures like generative diffusion models, there is now work that shows that there are generalizations of the Hopfield network. So not this network, a more generalized version from which transformers would emerge, from which diffusion models would emerge. So you may want to think as a physicist, because we like unifying principles, that Hopfield networks at large are a unifying principle. Okay, so now let's do the same for restricted Boltzmann machines. One slide intro to restricted Boltzmann machines. The restricted Boltzmann machine is same idea. We have recurrent neural network. It's again, it's inspired by Hopfield in a sense that will become apparent in a second. However, we restrict the connectivity such that we have one hidden layer and one visible layer. The input is going this way, the output is going this way. And at the time, hidden layer is a confusing concept. But if you want to think about the value of a hidden layer, really, so the Boltzmann machine is just a stochastic version of Hopfield. So you can think about Hopfield being the T equals 0, temperature equals 0 state of a Boltzmann machine. And a Boltzmann machine is just a finite temperature. And the restriction when I do a restricted Boltzmann machine or an RBM is just I say, look, my network is going to be restricted architecturally to one hidden layer and one visible layer. So what's the value of that hidden layer? If I didn't have a hidden layer, I just had one visible layer, and I'm training my data with that visible layer, you can think that the visible layer is trying to learn some correlations in the data. These are the apparent correlations, but there might be higher order correlations. The idea of having a hidden layer allows you to indirectly, implicitly figure out these higher order correlations, right? Of course, if you have more hidden layers, will be better. But at the time, they didn't know how to do that. So what happened is at its inception, a restricted Boltzmann machine was a single hidden layer, a single visible layer, and then we have the data, and we try to train that model using an energy function. I just added this term. It was also present in the Hopfield network. I just ignored it because I didn't want to complicate the discussion. So this is still a spin model. In modern machine learning, the W's are the weights and the B's are the biases. And what we do is we now have a probability distribution. We want the data that we're training on. We want to create a network which will correspond to a probability distribution where the data we trained on has maximal probability or has some other feature we're interested in. We want it to be the most likely observations of this probability distribution. We want to have other constraints on it, whatever. And we just have a Boltzmann distribution, hence the Boltzmann name. But now that's a generative model, as opposed to Hopfield's model and its inception, which was not a generative model. It was more of an associative memory, or if you want, you could use it for classification, for reconstruction. What does a generative model mean? It's actually a very powerful idea, which at first sight sounds completely insane. Generative model is a model that you give it samples, and then you say, the samples belong to a true probability distribution. I don't have access to this probability distribution, right? I want to learn that generating probability distribution. My samples are in very high dimensional space. So I do some crazy stuff. That's what happens nowadays in diffusion. You do some forward diffusion, backward diffusion, and somehow you did a process, you did exactly the inverse of the process, but you don't get identity, you get something else, right? So that's why I'm happy to dig deeper into this discussion, but that's why this is really interesting. This model is a form of a generative model, because if I learn this probability distribution, then I can sample new states. I don't have to sample the data that I trained on. I can sample something that is slightly less likely, right? Because I have the full probability distribution. So that's the power of that thing. The significance of this, well, if we talk about the physics, well, it's just really statistical mechanics. It's really Boltzmann distributions, nothing super fancy. And the consequences, to my understanding, is when Hinton did this, this was still an academic endeavor. But then in 2006, he thought of the idea of taking a restricted Boltzmann machine, which is that thing, and then taking the outputs that come out of this and treating that whole thing as another hidden layer in another restricted Boltzmann machine. So there's some non-trivial recurrence. And he did this over and over by stacking these. You can think about this as stacking these restricted Boltzmann machines. And he showed that you can do dimensional reduction very effectively, right? Which nowadays we know dimensional reduction is one form of autoencoders. And so whatever they learned in that step, there was a lot of hacking in a sense, if I may. It's not how we train modern networks, but you could think about this as the first inception of a deep neural network that, through iterative processes, Hinton and others discovered how to train and operationalize in a large scale way. So really, I think this is a very important contribution from that perspective. That neural networks are one form of extensions of restricted Boltzmann machines. So you might ask what kind of allowed neural networks to go that far as we are today. So there's a lot of different answers here, and I'm just gonna list some. I'm not gonna say everything. So everything in this field, to me, or not everything, but a lot of development that happens in this field is empirically driven. There's a lot of data, and if you want to get the right attention, you want to demonstrate your method works. And so there's a lot of tricks.
What's dimensional reduction?
Dimensional reduction means I have data that lives in very high dimension. So it's not 3 dimensions, like images, for example, like the C4 images, 32 by 32 by 3, right? They're pixels. And I would like to get some low dimensional representation of this data, right? Imagine I wanted to have a map from text to images. I wanted to write to a model, I would like a picture of a cat wearing a hat. You want the model to understand that this low dimensional representation corresponds to the high dimensional representation of cat wearing a hat, right? Cat and hat of colors and pixels. So you need some map to do this. That's what dimensional reduction does. Okay, so there's a lot of different tricks that happened over the last 10 to 15 years that explain the successes of modern neural networks beyond restricted Boltzmann machines. A lot of these tricks are not well principled. They are not very well understood. They make sense if you run code and they just work, like batch normalization, skip connections, skipping some of the connections in a network, carefully initializing the weights and biases that you want to learn. So this is to say that, of course, these are major reasons for why things work nowadays, but there's also reasons to start inspecting and thinking, why actually should we be doing this? And I think there's room for principled science, i.e. physics, for example, in doing so, that, like I'm going to show you in the next couple of slides. So this brings me now to the physics and AI, the now and tomorrow. And let's focus on now. So clearly, AI has been impactful in physics in a number of ways. That's also what the Nobel Prize Committee states. I am not an astrophysicist or a cosmologist, but there are experts here in the audience. And there's one postdoc who's been talking to me, and he tells me about work with optimal transport and diffusion models, where we take data, observed data of the current universe, and we can kind of roll it back or back diffuse it to the early universe and get very good images of the early universe, right? So that's kind of one area. I'm sure there's much more in astrophysics and particle physics than this. So please, this is not an exhaustive list. Condensed matter, there's a lot of things going on, especially with connections to first principle methods and density functional theory, but also the idea of using neural networks as neural quantum states. In a one-liner, there's just the idea of using neural networks as variational states for the wave function. And then we're just optimizing over the weights and biases because we want to find variationally the ground state solution. And definitely there will be more that I can list in one talk. But on the other side, how much physics have helped you with AI? So I did mention how associative memories could be viewed as a unifying principle. Hopfield worked on this, Krutov, Leon Boteau. Leon Boteau is a machine learning researcher, is not a physicist. But also the scaling laws by Jared Kaplan. Jared Kaplan is a physicist from Johns Hopkins and collaborated with David Polland and probably other members of the audience. And what they did in this simple paper, and also Hoffman and others, is to realize that the loss on test data, so when you do these experiments, you have a loss function, that's the energy function in our language. We're trying to minimize that energy function. So we're trying to minimize the loss. And then the optimized loss is the minimum loss that we can achieve. And we do this on test data. That's the data that we're have not trained on. So we see if our model is basically learning on unseen examples. Okay, that's kind of what we do in this field. And then observe that the test loss on the log scale here follows a straight line and has power law exponents. So of course, this was a big deal in this community because that told them at the time that means that if you increase compute, so if you have more computers, more GPUs, you will do better. It's not scaling exponentially, right? So they're just a way for them. If this experiment cost them, these numbers are not to scale, but if this experiment cost them a few hours, this experiment could cost them here out of scale, could cost them a few $1 million. They don't want to run a grid over all the parameters of the network, and each grid point corresponds to a simulation or an experiment that will cost a few $1 million or a few $1 billion. You don't want to do this. So you want a predictive model that, given small computations, will tell you which parameters to use at large computations. That's what this has done. But also, this type of thing suggests that there could be phase transitions in the loss dynamics or in the loss landscape, because the power law will change depending on the model architecture. So that gets me to the tomorrow. What could there be for physics and AI in the future? So I'm just imagining here, this is my subjective view. I could be wrong about this. But I kept emphasizing that many of the developments that happen in this field are not fully understood. I don't mean any disrespect to our colleagues in computer science and statistics. I think they're really doing great work, but their goals are different from our goals. Computer science, a major thrust is algorithmic advancements and making things more efficient and making things work, which is very important. In statistics, I think there's a lot of focus on being statistically principled, bounding errors, bounding behavior. Physics, our goal is slightly different. Our goal is to get something that behaves in some way. That's what we observe. And we want the minimal effective model that describes it. We want to get a description where we understand, we can kind of 2 lines explain to everyone why that behaves this way. I think there's hunger for this in that community. I think there's already folks who do this in academia, and I think there's more room. But if I want to list some examples of things I am thinking about myself, right? And then that's again biased by my own points of view. I think physical data is very different from language. If I want to use a large language model to do physics, whatever that means, I mean, the large language model is trained on text, so why do we hope that it will do well on physics and equations? And I will show you in one slide proof that actually language models don't do well on physics, which should be a point of pride for us. How about toy models of learning, right? These architectures, there's a lot of hacking that goes into building them because they're built with an eye for engineering, which is great. These folks are definitely smart. But if we step back and take these architectures and minimize them and look at them as toy models, as we do in condensed matter physics, and we start, playing with things, killing parts of the model, freezing parts of the model, and letting one thing only change at a time, I think we will provide important and pertinent information about how how these things function. If you look at the optimization, these power laws, there are works now by physicists, or you could say ex-physicists who work in DeepMind and other companies about how there are phase transitions that happen in these models. That's interesting theoretically, but also it's interesting because different models are in different regimes. So these predictions that are going to cost millions and millions of dollars are very sensitive to which regime you're in. And having a principled, well thought out approach is going to be very useful for saving money, right? So it's useful in a practical way. Learning phase transitions. So I don't mean here by I want to learn a phase transition, I mean phase transitions in learning. If you want to learn, if you want to use a model to learn some behavior, it's a known observation that if you train for too long, or you don't train in the correct way, I'm not going to specify what that means, you don't learn, you memorize. So you have something that memorized your data. But if it sees any new example, it just does not know how to interpolate in this example. And that happens in a very non-trivial way. How does that happen? Like there could be a phase transition in this learning from memorization to generalization that it's happening in these models. And finally, in physics, as theorists, I believe that's true for experimentalists too, but mostly for theorists, when I build a model, I want a model where I take the model, I use it to study an unexplored regime. So if I want to use machine learning, I asked myself that question many times. I don't really want to make a prediction and then go check, go run a complicated simulation, Monte Carlo, or exact diagonalization or whatever to check my result. How is that useful for me? What I would like is I would like to use machine learning in regimes which are easy for me to study, for example, weak coupling, and extrapolate to strong coupling. But then that's a problem because these models are not built to extrapolate. There is work actually going on nowadays in academia, in the machine learning community, trying to bound how we should think about extrapolation in these fields. So these are examples from my work on extrapolation. This is from 6-7 years ago. So we studied multiple models of phase transitions, but this is a very simple model. We teach our undergrads this model. This is a Heisenberg ferromagnet. So at height, this is the free energy. I'm just showing you the free energy. When T is larger than Tc, the m squared term will dominate. So I will have a quadratic energy function. And my minimum is at zero magnetization because I don't have an ordered parameter. I have not ordered. But as I lower the temperature below Tc, the m quartic term will grow. And then I will get a double minima. And that corresponds to a phase transition to a ferromagnet with finite magnetization because now the minima of the free energy are at minus m or minus delta m or plus delta m. Right? That's what we know this model very well. So what we did in this paper, we took a Gaussian kernel. If you don't know what that is, just a basic form of regression. And we trained the free energies when T is larger than Tc, when the m squared term dominates. So this is the data. That's what we fed. And then we asked it to extrapolate as a function of T going below Tc. And it extrapolated the right behavior. And then we fitted the minima, and we plot the minima here, and we get the right phase transition. We did this for a bunch of other models that are not as trivial. But that's one example. I still don't understand why that works. Where I fitted something, right, in the regime that's very easy for me to understand, high temperature paramagnet, and the machine learning model figured that it should be a ferromagnet at low temperature. And I believe these models and these approaches could be done more and could be systematized, could be understood more principally, which is not what we've done at the time. At the time, we just applied this and we were fascinated that it actually works, right? And we didn't only do it for this, we did a bunch of other things. This is a more recent thing, which is kind of, it's a lot of work, but it's not really hard work. So back in time, our students used to do something called the comprehensive exam. So I did this as a graduate student. I had to go to my first and second year to a room, and I had to write an exam on 2 days. Each day is 5 hours. I'm given like 10 questions. They're really hard questions on, everything we should know as a physicist, and I just have to pass. And they didn't tell me I passed, but it didn't tell me what I did on the test. So I have no idea how I did. Okay, so I'm getting into machine learning, and I keep talking to experts, and everyone talks about how AI and LLMs generate code and can do amazing things for you, and they can solve math problems. And now they're hiring Terence Tao and professional mathematicians to write problems to beat LLMs. So I kept asking my colleagues, did anyone do this for physics? And they said no. So I said, okay, why don't we take? They said like there are multiple choice questions for like high school questions, blah blah blah, but nothing really devoted for physics. So we took these comprehensive exam questions. We took roughly 1,300 questions, and we automated the procedure, and we evaluated these models and also open source models. But these are the frontier closed source models on all of these questions. Here, the questions are classified by field. This is AMO, this is electricity and magnetism, classical mechanics, optics, quantum mechanics, statistical physics. And here you see, this is the validation set. So you train on some set, you validate on another set, and then you test on a set that has been reserved, that the model has not seen before. So what you want to look at is the test performance. And apparently in math Olympiads, many of these models get like 99%. So they can beat humans. But you see in physics, the best model is O3 Mini, which is the ChatGPT, the OpenAI model from January, gets 59.9% in university level questions. All other models go below 45%. Sorry? Huh? Yeah. Well, there's a footnote. There's a footnote in the paper where we say that this exam students typically get somewhere between 50 and 70%. But I wasn't sure if I should be saying that, right? So of course you could say that for a model to do this without knowing anything about it, it's not trained on this, right? That's pretty impressive. It may be comparable to, maybe, I don't want to say that. I don't want to make that assertion, but maybe comparable to a graduate student. But the reality is people approach these things as if they are super powerful, superhuman. We're in the matrix revolution. They have not reached that, at least for physics, right? Physics remains a difficult subject. And we analyze the errors. They're funny. You could look at them in the paper. They'll be entertaining to read at night. And the errors are sort of like, so when you do this, one of the ways you do this is you tell the model to self-reflect. That's how it can improve its performance. So it starts thinking out loud and it starts backtracking and saying, oh, I should not do this. And in many of the errors, the self-reflection keeps going on forever. It just keeps reflecting and goes nowhere. Or it makes silly mistakes, like it does, a very complicated computation, and then it wants to, you want it to do the expectation value of P, the momentum to the 4. And then it decides on its own that P to the 4 is the expectation of P squared squared. Right? So there are definitely mistakes that suggest it's not very smart. Like, I don't know how, when it does the right things, it does it, right? It's a lot of association in a way that sort of luckily works out, but I really don't know. Okay, so I hope I'm probably above time, but I want to just give you some references to Hopfield and Hinton's work. And finally, I want to leave you with some quotations from the Nobel Prize website. I just highlight in blue about Hopfield's model. The Hopfield network utilizes physics that describes a material's characteristics due to the atomic spin. And then in Hinton, they say he used the Hopfield network as the foundation for a new network that uses a different method, the Boltzmann machine. And then, of course, the Nobel Committee, the Nobel Prize Committee, highlights how AI has been very useful in physics research, i.e., for example, in material science. But I hope I convinced you that there's more that you can do in this area. Thank you.
All right. Thank you very much, John, for a really interesting talk. So we have time for questions from the audience.
Thank you for the talk and taking on the challenging task of discussing something that's not, exactly your own field. At the start of your talk, you mentioned maybe an analog to data fitting, to curve fitting. Could you say more about what analog you had in mind?
Sorry, my slides are frozen for some reason. Let's see. Oops. I don't know what's happening. Okay, I can just answer the question without the slides. So one way to think about neural networks and neural learning is I just have a class of functions that allow any nonlinear behavior in the data to be learned. So I'm really trying to fit, but it's just in very high dimensions, this nonlinear structure, right? So it's really at heart, it's that. The tricky part is oftentimes in high dimensional data like this, there's a lot of noise. And you don't want to fit to the noise, right? Because your data might not be physics data, right? Might be some the market, some stock market price, and there's a lot of fluctuations, or someone, when they're tabulating the data, they made mistakes. And so there's an art in how you avoid fitting to the error and fitting to the signal, so that when you're offered a new signal, you make the right prediction. You don't make the noisy prediction. Does that make sense to you?
Sure. Thanks.
Thank you. I had a question about, you mentioned that there's more to be learned about how phase transitions are occurring in the behavior of neural networks. And I'd be interested, are there cases that have already been studied where there's an important phase transition in the behavior and there is some sort of like minimal model of how and why that's happening? I would like to learn more about that.
Yeah, that's a great question. So, like I said, you should view this talk as my own personal view of why that's interesting as someone who's trying to enter that field. So I'm aware at least of one paper that appeared in December by ex-physicists and mathematicians. So the last author is Jeffrey Pennington, who is a high-energy physicist who now works in DeepMind. And basically, there is an observation in this Hoffman paper that I am not writing to you, I'm not showing you here, so you just have to believe me, that there is a universal scaling law. The power laws all turn out to be related to the data. Language has power law statistics. There's something called Zipf's law. And so the power laws in the language translate to the power laws you see in the loss. So that's something they understand. But there is one type of scaling law that does not depend on any power law in the data, just a universal number, roughly a half. And why? I don't know. So that paper by Pennington, they studied a linear regression model. So you can think about it as a form of a linearized model of the real model. So it's kind of a toyish model, still very complicated. Used a lot of tools from random matrix theory, because they are random matrix theory experts. There's a lot of simulations. And they showed that there's the loss is continuous, but it has cusps corresponding to the phase transitions as they tune different exponents in the model. Like I told you, the exponents come from the data itself. And in these different phases, there is a universal scaling law that sits in one of them or in multiple of them. And they have the math, it's all solid, but I probed them many times of, do you understand why that's the case? And they don't. So I think, that's one minimal example of such a thing, which is quite relevant right now to actual practical work, and it's not fully understood.
Thank you.
Hey, thanks for the talk. I actually tried doing quantum field theory using ChatGPT, and I was trying to renormalize a particular theory, and it did not give good results, as some examples that you mentioned. But then when I fed in my calculations that I did on LaTeX, and then gave it some hints, it kind of went towards the right answer. And about after 2 hours, it gave me the right answer. Now, all of this, what I did was training the model in real time as to giving it hints and then making it think in a certain way. Now, when you were talking about phase transitions from paramagnetic to ferromagnetic, how did the model really understand spontaneous symmetry breaking, or how did it know how to choose that and give you the correct potential? Because you mentioned that doing math questions, it's easy, but physics, you require this intuition that you need to build. So how do you go about doing that and training your data?
Yeah. So let me be clear about something. In this case here, we did what you did, okay? Except that we automated the process and we didn't help it. I agree with your experience. If you work very hard with these models and you kind of break it down and write the steps, they will help you. The issue is a lot of times when you don't do that, They will pretend that they're helping you. They'll might convince you that they're right and they're wrong, right? So that's this study. This study has nothing to do with large language models. This study is really taking a Gaussian kernel and fitting data from the free energy at high temperature. There's no LLM that I'm prompting. I'm not asking anyone any question. I'm really doing fitting, but instead of doing the standard thing where I interpolate, right? And you could think about extrapolation as interpolation in high dimension, because in high dimension, it's very hard to tell the difference. Here I'm in low dimension, right? This parameter space is what? 2-dimensional, okay? Instead of interpolating like I should have, I extrapolated. And yeah, I mean, it doesn't get me exactly accurate results, but it gives me pretty good results. And why is it doing that? That's exactly what I'm trying to advocate in this talk, that we should try to understand that if we want to use machine learning as something that's beyond data processing and as an actual, method for solving problems in physics, then we need to understand how to use and to extrapolate. Right? So I don't know the answer to the question yet. I hope I will.
I see. But do you think perhaps training it, I don't know, a very rudimentary example, giving it a textbook and then telling it to learn that particular concept, or giving it the papers and then feeding it data, do you think that might refine the system further to think about physics problems?
Yeah, if you want to think about LLMs in this way, you would be fine-tuning it on physics. And I think it will do better, but that's not what the goal is. The goal is we will have an agent that will learn everything in the universe and can do everything. That's at least what people who talk about AGI, artificial general intelligence, say, right? But of course, for some domain-specific thing, of course, you can fine-tune it. And because it will have encountered these problems many, many, many times, when it's trying to do text completion, it will do it better, right? So I don't know if that really solves the problem in a profound way.
All right, thank you.
You had mentioned that maybe other architectures are better for things other than language learning. Can you give an example of other approaches people are taking in other domains that are maybe better at generalizing in the kind of way that we would want a physicist to do?
Yeah, I mean, that's a good question. So I don't have a very clear example. What I meant is the following. I will give you some examples, but it's not really examples of what you're asking me precisely. What I meant is when people build these models, they had in mind text, which the context here is I have a context, a sentence, and I want to complete the next word. Or I have images, but physics is neither. So trying to fit it in that is not a good idea. A good example I know of someone in the audience is using optimal transport to learn the early universe, but using a loss function that's inspired by physics. Not using a loss function that's inspired by what you should do in machine learning. Works better, right? Because it's supposed to optimize for the physics, not optimize for the data. You see what I mean? So we need but what I'm posing, I suppose, is if we want to use these models, let's not use them as a black box. They're not super hard. We can learn them and we can adapt them, go beyond them, expand upon them, whatever.
Oh, thank you for the great talk. About the scaling law, I think another message of scaling laws is that as we increase the size of models and data sets, the law of inductive bias or human prior knowledge is not required anymore, like something like happened in Peter Lassen of Richardson. So in this context, do you think the statement physics has room to contribute to AI still holds true?
So yeah, I don't fully understand the statement. You're saying human bias or inductive bias is gone?
Like putting physics into understand AI more.
Yeah.
So like that graph just says like, let's just increase the data set and let's just increase the model parameters, then it'll be better. So we don't need to put any knowledge into the model and just put a lot of data and whatever into it. But in this context, like, how do you think about?
Yeah, but you could ask, for example, the scaling laws, the paper that I mentioned to your question earlier, the power law changes depending on the statistics of the data, right? So this figure tells you, given a certain power law, how I should extrapolate. But there could be other power laws. So the loss could be changing behavior as a function of parameters. So when I say physics has role to contribute, I don't mean that we should open the model at very large scale and try to analyze it. I think that's hopeless. We don't even understand 2-layer or 3-layer models. Are we going to open, these huge models that no one can mess with, that we don't even have access to? I mean, simply understanding this phenomenology is not fully done, right? And you might want to call it physics, you might call it optimization. I think our goals are not, if I present this as a goal, it's not different from the goal of the applied mathematician or the computer scientist or the statistician. The only difference is in the perspective. If you read these papers, they're written with a certain philosophy or certain mindset that's very different from the way we think about physics. In physics, really, I like this example a lot in physics. When I was a PhD student, I had one time a very nice result, and I was excited about writing a paper. And then I told my advisor, and she said, well, why would you do that, right? You have no explanation. It's not computer science. Right? Now, I don't mean any offense to computer scientists, but really, if I did that, now that I know, PRL would just reject my paper. The reviewers, I will have no chance, right? Because it's not about getting the best numbers. It's really about explaining why what I found makes sense. Do I have a model for it? A model of the model. I think that's really the perspective that is missing there. And it's not because those folks are not capable. They just don't think this way. They don't care. They just want to prove everything they can prove or improve algorithmically efficiency. And that's it.
Thank you.
Does that get me closer to?
Yeah, right. I mean, my question was like, maybe machines don't think physics in physical way. They just think in their own way. And physics may be humans' way of interpreting something. Then, yeah.
You think we're going to have an inductive bias because of the way we think in physics terms, or?
Yeah, it's different from how machines interpret the world.
Yeah, but then I think that's a more philosophical question about,
Yeah, right.
is science the absolute truth or our perceived truth? So
Okay.
let's leave that to some other
Yeah,
historian.
thank you.
or-
Thank you.
All right, maybe one more question for John. Any questions from the Zoom audience? All right, well, if not, then why don't we thank John again for a fantastic talk.